Welcome to a sim code. Welcome back. If you're enjoying the video, be sure to like and subscribe. The Fast Fourier Transform, FFT, in Python is a powerful algorithm used to convert a signal from the time domain into the frequency domain, allowing us to analyze the frequency components of the signal. It is typically performed using NumPy, FFT, which takes a time domain signal as input and returns the frequency domain representation as complex values. These values represent both the amplitude and phase of different frequency components in the signal. We can use numpy.fft.frec to generate the corresponding frequency bins for the FFT output. By plotting the magnitude, absolute value, of the FFT result, we can visualize how much energy is present at different frequencies. FFT is widely used in signal processing, audio analysis, communications, and various other fields to break down complex signals into simpler sinusoidal components. Let's start by importing necessary libraries. We will use NumPy for mathematical operations and plotting. First, we need to create the square wave signal. A square wave alternates between -1 and 1, and we will sample it at discrete time intervals. We will generate a time array and create the square wave signal based on it, setting the sampling rate in samples per second, hertz. We will also define the frequency of our square wave in hertz. Sampling rate, samples per second. Frequency of the square wave in hertz. Number of samples. This will determine how much time we cover. We want 1 second of data. Time duration for our signal in seconds. Total number of samples, which is the sampling rate times the duration. Generate the time vector. NP linspace, start, stop, number underscore samples. We start at 0, end at t, and we need n samples in total. Time from 0 to t, 1 second, with n points. Generate the square wave using a mathematical function. We use np.sine to create a square wave, alternating 1 and -1. np.sin gives us a continuous sine wave, but np.sine will turn that into a square wave by converting positive values to 1 and negative values to -1. We will base it on the frequency of the square wave. The square wave will be the sine of a sine wave with a certain frequency. Now, let's plot the square wave to visualize it. The square wave will look like alternating high and low values, 1 and -1. Now, let's compute the fast Fourier transform, FFT, of the square wave. FFT will transform our time domain signal into the frequency domain. np.fft.fft performs the fast Fourier transform. It takes the square wave signal as input and returns the frequency components of the signal. Let's calculate the frequency bins corresponding to the FFT result. The length of the FFT result is the same as the number of samples, n. We need to create a frequency array to map the FFT results to corresponding frequencies. np.fft.frec n d returns an array of frequency bins for the FFT result. The second parameter d is the sampling interval, inverse of the sampling rate. Now, let's plot the magnitude of the FFT result. We need to compute the magnitude of the FFT, for example, the absolute value of the complex numbers. We take the absolute value of the FFT result to see how much power is present at each frequency. The FFT result is symmetric, so we only need to plot the first half. We will slice the result to get only the positive frequencies, since the FFT result is symmetric. Half the length of the FFT result. Get only the positive frequencies. Get only the magnitude for positive frequencies. Plot the magnitude of the FFT versus frequency. Detailed explanation of what we see. The FFT of a square wave will show spikes at the fundamental frequency and its odd harmonics. This happens because a square wave can be represented as a sum of sine waves, Fourier series. The harmonics are integer multiples of the fundamental frequency, but only odd multiples appear. This is the key property of a square wave's frequency content. Let's add some more comments to clarify. Why does the square wave only have odd harmonics? The square wave has a symmetric shape, which means it can be broken down into sine waves with odd multiples of the fundamental frequency. This happens because the square wave is an odd function. It's symmetric about the origin but flips signs. For example, if the fundamental frequency is 50 Hz, we will also see spikes at 150 Hz, 250 Hz, etc. Additional note, the magnitude of the harmonics will decrease as we go up in frequency. This is because the higher-order harmonics contribute less to the overall shape of the square wave. Let's clean up the explanation further. A square wave contains only odd harmonics. The amplitudes of these harmonics decrease with frequency, inversely proportional to the harmonic number. This is an important concept in signal processing, as it shows how complex signals can be constructed from simpler ones. Final thoughts. In this code, we 1. Created a square wave using np.sine, np.sin. 2. Performed an FFT on the square wave to analyze its frequency content. 3. Visualize the results in both the time domain, square wave, and the frequency domain, FFT magnitude. The Fast Fourier Transform, FFT, is an incredibly powerful tool in signal processing. It helps us break down complex time domain signals into their frequency components, which is crucial for many applications, such as audio processing, communications, and image analysis. Thank you for following along. Let me know in the comments if you have any questions or if you'd like to see more tutorials on this topic. Now run our code. I hope you had fun. Hit that like button and subscribe for more awesome videos.